answer is that prove that x and y are independent of each other actually. X and y are independent of each other. So the key problem that we will like to do is that are x and y independent? Are x comma y independent? In other words, that the number of females that visit the post office is independent of the number of males that visit the post office if the both males and females have what do you call these probability distributions actually. Okay, so the answer is yes actually. Okay, answer is yes. Okay, and the question is what is the proof actually? So what is the proof? So here is a quick discussion over the proof actually. Now, what? Now, what? Now, in order to show that x and y are independent, we need to show that the probability that I males visited the post office on that given day and J females visited the post office on that day. This probability should be equal to the probability of x equal to I and the probability of y equal to j. So these two independent, what do you call, probabilities. So this is what that we are interested in to show. Okay. Now, what would be the probability that x is I and y is j? Okay. I can write this probability as the conditional probability. So I can say that this is same as the probability that x is I, y is j given x plus y, the total number of people. So you have to also keep in view that it is also given that the total number of people has also the Poisson distribution. So within that total number, males and females also have a Poisson distribution actually. Okay. So let's try to write that probability that x is I, the males, I people visited, the I males visited the post office and j females visited the post office, given that x plus y equal to I plus j, okay, times the probability x plus y equal to I plus j. Okay, so I just wrote this as what do you call the conditional probabilities. Okay, so I'm writing it a bit different that the book actually. So the book applies what do you call one version of law of probability, so you can read it from there. So I'm just interested in this what do you call particular expression actually. Now let's compute this probability and let's compute this probability. Now, if x is the number of people that visit x is the number of males that visit the what do you call that particular day to the post office, and y is the number of the people that visit that particular day to the post office, then what would be x plus y? The meaning of the x plus y is going to be the total number of the people that visited the post office on that particular day. But we know that the number of people that visit the post office on that particular day is the Poisson, has a Poisson distribution with the parameter what do you call lambda. Okay, with the Poisson distribution with what do you call lambda. So if this is the case, then we know the explicitly probability of x plus y plus y equal to I plus j. So this is a random variable whose distribution is this. So we're going to use the PDF of the Poisson distribution with the parameter lambda, and that distribution is e to the minus lambda times lambda power I plus j, in other words the value that it takes, divided by I plus j factorial, divided by I plus j, what they call factorial. So this is what is going to be the case. So what is the next thing? The next thing is, so we know this probability, and now let's think about this probability. Let's think about this probability. Now, given that, so imagine that given that there are I plus j people who have visited the post office on a particular day. What is the probability that there are I males and j females? Now the number of people, every person that visits the post office and looking at its gender is like doing a Bernoulli trial actually. Okay? It's doing a Bernoulli trial where a person can be male or female. So we are doing I plus j Bernoulli trial. Okay? Okay? And out of that, there are, say, I males and I females. So if you associate, for example, your probability or success with, say, for example, females or males, okay, any one of them. So this is like the binomial distribution actually. Okay? This is like the binomial distribution. So you have your n is I plus j, okay, and your probability is what? Is really p actually. Okay, so it's p. So if you have I plus j, so you know that I plus j persons has visited the post office. So each person can be male or female. Then what is the probability that I persons out of it are males? And if the I persons are males, obviously the j are females actually. Okay, so if you associate your success with this, so you can say that the probability that x is I and obviously y would be j if you know that x plus y is I plus j is going to be equal to what? Is going to be equal to the Bernoulli binomial. You can model it through binomial distribution of this actually. So that out of I plus j, say I people are males, okay, and probability of each male is p, so the I males is going to be p to the I, and the probability of j females is going to be I plus j minus I and j. So this is what the probability is. Now once you know these two probabilities, so I know this probability and this probability, so I can write now explicitly this probability. So the probability that x is I and y is j is going to be I plus j times I p to the I 1 minus p j times e to the minus lambda and lambda power I plus j and everything divided by I plus j factorial. So this is what is going to be the case actually. And what you can do, I mean, you can explicitly write this. So I plus j factorial over I factorial times j factorial. So the I plus j factorial and I plus j factorial will cancel out. Okay. I plus j factorial and I plus j factorial will, what do you call, cancel out. And what will remain, okay, so what will remain is going to be what? e to the minus lambda. This is the first factor, and so I have lambda. So lambda is I plus j. So one lambda power I can be combined with lambda p power I. So I can write this as lambda p power I, okay, over I factorial j factorial times 1 minus p can be combined with lambda power j. So it's going to be 1 minus p times lambda power, what do you call j actually, okay. I must write this. So this is really different actually. So the next step is this. So this is what that you're gonna get. Now the last thing that you need to show we are almost done actually, because if you see, even e to the minus lambda can also be broken up, okay. E to the minus lambda can be broken into say e to the minus lambda p, okay, times lambda p, okay, power I over I factorial times e to the minus lambda 1 minus p times lambda 1 minus p times j power j over what do you call j factorial actually. Okay, this is what it's going to get. But if you remember, it is also known that x and y okay, it is not also known, so we need to deduce actually. So if it is known, we are done. So we need to, because this is kind of represents if x is known to have what do you call the Poisson distribution with probability lambda. So this is really the probability of x equal to I. This is really the probability of y equal to j. But what we can deduce from here also is that x and y both are Poisson random variable, and they are also independent actually. Okay. So now I would like to deduce what is probability of x equal to I. Okay. So we yesterday write actually that if you know the joint PDF, then you can deduce what you call you can apply, or maybe I can apply what you call the law of the total probability, and I can say that so when x is I, so for j I have several possibilities. So j can be 0, j can be 1, okay, and so on and so forth actually. So in other words, that I can say that this is going to be a sum that goes from j equal to 1 to infinity, probability of x equal to I and y equal to j actually. So I need to compute this sum. But I know that this probability is this actually. Okay, so this probability is this. So if I take this expression and substitute it here, and this sum is on j, so I can pull this, all of these terms out of this sum because there is no index j here actually. So I can write by substituting these value and by pulling this out of the expression, I'm going to get e to the minus lambda p times lambda p raised to I over I factorial times j equal to 1 to infinity, and e to the minus lambda 1 minus p and lambda 1 minus p raised to j over, what do you call, j factorial. So this is what that you're going to get. And this can also be written as what? I mean, if you see, this is the sum of the probabilities of the Poisson random variable with the parameter lambda 1 minus p. So it is the sum of all probabilities of the Poisson random variable with the parameter lambda 1 minus p. So if it is the sum of all probabilities of the Poisson random variable with the parameters lambda 1 minus p, so this sum must be equal to 1. So this entirely should be equal to 1 actually. And hence the probability of x equal to I is this quantity. So if the probability of the male being I is this probability, that means that x has a Poisson distribution with parameter lambda p. So this is what that we deduce actually, hence. Okay. Then we can do one step ahead. I can play the same game with y. So in other words, I can say that let's compute what is the probability of x equal to j. So let's compute what is the probability that y is j. So I can write this as sum that goes from I equal to 1 to infinity, probability that x is I and y is fixed j actually. And I know about these two probabilities, so I can take these two probabilities and substitute it here. So once I substitute it here, so what you're going to get? So you're going to get I equal to 1 to infinity. This sum is on I, so I can keep all of these j terms out of what you call sum actually. So let's keep this e to the lambda 1 minus p times lambda 1 minus p times j by j factorial, okay, and keep inside I equal to what do you call 1 to infinity, okay, and e to the minus lambda p times I divided by what do you call I factorial. Now again the same argument. What does this represent? This expression represents that this is the sum of the all probabilities, okay, of the Poisson random variable with the parameter lambda p. So if it is the sum of all probabilities of the Poisson random variable with the probabilities p, this must be equal to 1. And how about this? So this shows that probability of y equal to j is this expression. In other words, the PDF of the y is this expression. And if the PDF of y is this expression, then the y would be a binomially distributed, not binomially, it's going to be a Poisson random variable with the parameter lambda 1 minus p actually. Okay. So this shows x has a Poisson distribution with the parameter lambda p, and y has a Poisson distribution with the parameter lambda p. And using this equation, we also deduce that probability of x equal to I and y equal to j is equal to, this is the probability x equal to I, and this is, we just proved that probability y equal to j. And what does this also shows? That x and y are independent. X and y are independent random variables. So this is what it shows. So what we ultimately show, that if we assume that the number of people who enter in the Poisson in the post office has a Poisson distribution with the parameter lambda, then the number of the females and the number of males among that total number of people are also going to have the Poisson distribution, okay, with the parameters lambda p and parameters lambda 1 minus p actually. So this is what it shows. And these both quantities are also going to be independent, and this meets with our intuition, because obviously the number of females that visit the post office should not depend on the number of males that visit the post office actually. It should be independent actually. Okay? So we did this stuff actually. What is the next thing that we are going to consider? So it's really going to be a kind of a continuation of what we did. What we're going to do now, we're going to discuss different distributions, the sum of two random variables. So we're going to take, say for example, a random variable x and then a random variable y and consider their sum. Okay? So we'll consider that if x is binomially distributed and y is binomially distributed, is x plus y is also binomially distributed. So if x is normally distributed, y is normally distributed, is x plus y normally distributed? So x is Poisson distribution and y is Poisson distribution. Is x plus y Poisson distribution? We had a glimpse that yes, at least in the case of the Poisson distribution, you know, it almost makes sense actually. So this is really the converse of it, that okay, if the sum of the two random variables is Poisson distribution, follows a Poisson distribution, then each one of them must also be Poisson actually. Anyway, so we want to consider the distributions of the sum of the random variables actually, okay, following certain distributions. So we will start with the uniform distribution and then we will move to what you call the more sophisticated distributions. All right. Let's have some generic comments. So what is the next topic that we would like to do? We would like to consider the sum of two independent, really the converse of what we did actually in different kind of distributions. Sum of the two independent, sum of two independent random variables. Okay. So in other words, if I know the distribution of the random variables, what would be the distribution of the sum of the two random variables? Okay. So here are some generic comments and then we will get into the concrete situations actually. Okay, so suppose that x is a random variable, is some random variable with PDF fx, and y is a random variable with PDF fy, and maybe we assume that the CDF is fx and CDF is fy, and their joint PDF is fxy and the joint CDF is fxy. Okay, so this is what is the notation actually. So what is the next thing that I would like to show? The next thing that I would like to show is this. So I would like to show that, so what we would like to consider, or what we would like to have, we would like to have a formula for the CDF of the sum of the such random variables and the PDF of the sum of the such random variables in the terms of these quantities. In the terms of these quantities, okay, with these 4 quantities. This is what that I am interested in. Now, let's start with say fx plus y and evaluate it at a. So try to consider what you call the CDF of the random variable x plus y. Okay. So x plus y means what? What is the probability that x plus y is less than or equal to a? Okay. In order to compute this probability, what you need to do? You need to compute the integral, okay, of the joint PDF of fx of fy with respect to dx with respect to dy over this, what do you call, region x plus y less than or equal to a. Okay, so over this region R that is spanned by x plus y less than or equal to a. Okay. By the way, if you want to explicitly this region, that what would be this region x plus y less than or equal to a? So we need to plot, what do you call, x plus y equal to a, and what would be x plus y equal to a? So the x plus y equal to a is going to be the line that passed through a0, okay, a0 and 0a. So it's going to be a line that passes through such kind of a object. And so if this is x, this line is x plus y equal to a, so the water region would represent x plus y less than or equal to a actually. So if I, for example, take origin 0, 0 and substitute in this inequality x plus y less than or equal to a, then this might be true actually. Okay, this might be what you call true. So the picture that apparently I have made is really assume that a is a non-negative number, but this is not necessarily actually that a must be a non-negative number. It could be a negative number as well actually. Okay, so this is just a one indication of it. So what is the region that satisfies this inequality? Is this downward region actually. Downward region. So if you want to, for example, write this integral more explicitly, by the way, if x and y are independent, this would be equal to fx of x, fy of y, dx, and what do you call dy. Now in this region, x varies from where to where. So x varies from here, by here means negative infinity to this point, always negative infinity to this line, negative infinity to this line. So it starts from negative infinity and it goes up to, what do you call this, x plus y equal to a, and what is the value of x on this x plus y equal to a? So it's y minus a. So it goes from what do you call, it starts from minus infinity and it goes to minus infinity. How about y-axis? So the y goes from minus infinity to plus infinity actually, or minus infinity to plus infinity. So this is what the limits on x is actually. So what can be done? I can I can pull this fy of a out of it because, you know, the first integral is with respect to x, so if I wish I can pull this fy out. So I'm going to have minus infinity to infinity fy of y, and what is going to remain is minus infinity to y minus a times fx of x dx, and everything multiplied by dy. So this is what that you're going to get at.